Here we'll continue our discussion in chapter 8. We're going to look at the conic sections and nonlinear systems now. A lot of the stuff we're going to do in the beginning of this section would be the review of what we've done already. As you recall, conic section presented in the chapters are as the form of ax squared plus dx plus cy squared plus ey plus f equal to 0, where either a or c must be non-zero. And we looked at all these shapes: parabola, circle, ellipse, and hyperbola. And there are some examples on the right-hand side. The characteristic of these are, for parabola would be either a is equal to 0 or c is equal to 0, but not both. For the circle, a is equal to c is not equal to 0. For the ellipse, a cannot be equal to c. The product of AC has to be greater than 0. For hyperbola, the product of AC has to be less than 0. These are just some examples. If either x or y is a square, we're looking at the parabola. In this case would be example y is equal to x squared or x equal to some y squared. For the circle, you see both x and y are squared and the sign in between are positive. For the ellipse, would be very similar to the circle, except would be equal to 1, and then we have some numbers at the bottom of the fraction here. And for the hyperbola, the difference would be, instead of plus, you have minus. All right, this would be an excellent place to pause and see if you can come up with your own answer before you view the solutions. You want to decide on the type of the conic sections, whether it is a hyperbola, parabola, circle, ellipse, and so on. And we have all these to look at. First one, x squared is equal to 25 plus 5y squared. We can rewrite this as x squared minus 5y squared equal to 25. Divide each term by 25, and we get it into this form. Once we get it to this form, this would be general form of hyperbola, because the sign in between is minus, both x and y are squared, and as you can see is equal to 1. If this were plus instead of minus, that would be an ellipse then. So this would be a hyperbola because we have a sign in between is minus, and this, the center would be the origin. There's no h and k here, as you can see. And we know how to graph them. Talked about the graph of hyperbola before. As you can see, this hyperbola opens on x-axis because this x comes first in the formula. And we form this rectangle here by knowing the center as 0, and we know a and b. And these are our asymptotes. The diagonal of the rectangle would be our asymptotes. Your graph is going to get closer and closer to its asymptotes. And as you can see, the vertices would be at this point here. -5, 0, and positive 5 zeros. The equation of the asymptotes can be written as y is equal to plus or minus square root of 5 over 5x. Next one. Once again, you already paused the session and you should know what this look like. You need to complete the square twice for x and y. You should already know how to do that. I'm not going to go to detail of that anymore. And looks like that we are looking at the circle here with the center at the point 4 and -5. So this looks like is a point because the radius is equal to 0. When the radius is 0, this would be just a point, just the center. If you had a different number than 0 here, then that would be a circle with that radius. So it's just a point. How about this one? So this could be a ellipse, circle. We need to complete the square to see what it is. Again, we should know how to complete the square. I'm not going to go over the detail of that. We do need to factor the coefficient of x squared and y squared and find what we need to add inside the parentheses. And once we do all that, as you can see, we get this form here. And if you recall, because of the sign in between is plus, it cannot be a hyperbola, so it's an ellipse. With the center being at 2 and -3, that's the square root of 9, a square root of 4, and that's the graph of ellipse. Next one, looks like x is a square, y is not, so it could be a parabola. Since only one variable is a square, which is x squared, the equation represents a parabola. Solve for y, and complete the square to get into general form. Again, we know how to complete the square already, so we skip through the details. As you can see, that would be a parabola, has a vertex of 3 and 2 and open downward. Next one, to see what this shape look like, we need to complete the square. You should all know how to do that by now. And here we get the minus. So it looks like it is the hyperbola. The center would be at 1 and 2, and that is the hyperbola that opens on x-axis. As you can see, x comes first, and that would be the shape of that. The conic is a set of all points in a plane such that the ratio of the distance from P to the fixed point and the distance from P to the fixed line is constant. The constant rate is called eccentricity of the conic, written as letter E. Ellipse and hyperbola have eccentricity, where C is the distance from the center to a focus. For ellipses, a squared greater than b squared, and c is equal to the square root of a squared minus b squared. So c would be between 0 and a. Then if I divide each term by a, you would get c over a is between 0 and 1. The e would be equal to c over a. E is equal to c over a. I'm going to use this in a lot of our calculations. Eccentricity, E, is equal to c over a. And what's important is E is greater than 1 for hyperbola. Note that the ellipses with the eccentricity close to 0 would have a shape of the circle. Okay, let's look at some examples. Find the eccentricity of x squared over 9 plus y squared over 16 equal to 1. Since 16 is larger than 9, remember the largest one would be the a. So a squared would be equal to 16, so a is equal to 4. You compare these numbers, whichever is larger, that would be your a squared. So a is equal to 4. If you recall, one of the formula that we were supposed to remember, c squared is equal to a squared minus b squared for ellipses. So if I take a square root of both sides, I can solve for c. I know what a and b's are, so I can solve for c here. So what is e? Remember we said e is equal to c over a. So all you have to just substitute the value. C is square root of 7 over 4. Now e is less than 1. When e is less than 1, so that would be the ellipse. If it's e is less than 1, that would be ellipse. If it's e is greater than 1, that would be a hyperbola. So in this case, find the e eccentricity of this equation. 5x squared plus 10y squared is equal to 50. So first thing you want to do is get into the form of general equation. By dividing each term by 50, you get x squared over 10 plus y squared over 5 equal to 1. So remember the larger number is a, so a squared is equal to 10, so a would be square root of 10. So from there we can solve for c. Now once again, e is equal to c over a, and then we find that is 0.71. Again, is less than 1. And confirm that is the ellipse. Now this page would be a good place to compare. If a is less than 1 or greater than 1, what would this shape look like? The first one, e is equal to 1 over 4, and then the next one is e is equal to 1/2, and e is equal to 3/4. All the shapes at the top, the e would be less than 1, so we refer to the ellipse. However, at the bottom row, e is greater than 1, 1.125, and that represents the hyperbola. So once again, if e is less than 1, is a form of ellipses. If e is greater than 1, we're looking at the hyperbolas. And you really remember the e, what's e is equal to? C over a. Find the eccentricity of the hyperbola. It's already given to me in that general form. So I can easily find what a would be. A is a larger number. A squared is equal to 9. A is equal to 3 then. Square root of 9 would be 3. From there, I can solve for c. If you recall, for the hyperbola, we had c squared is equal to a squared plus b squared. And so c would be square root of 13. We said e is equal to c over a. Now I know what c is, what a is, and then it would be 1.2. Again, this is larger than 1. That confirmed that e is larger than 1 for hyperbola. find an equation for each conic with the center at the origin and eccentricity E. For first one, they're given to us at the focus at 3, 0, and the eccentricity is equal to 2. So let's take a look at how we solve this. For part A, E is equal to 2, that's greater than 1. So we know this is a hyperbola with C is equal to 3. The focus is given to me as 3. So I can write E is equal to C over A. E is given to me, C is 3, so I can solve for A. What's missing is A. So now I know A. We can use the formula B squared is equal to C squared minus A squared to find B squared, and from there we have all the information to write the equation of the hyperbola. I know what A is, I know what B is, it's open on the center. So it looks like that x squared over 9/4 minus y squared over 27/4 equal to 1. We can write this as, move the 4 up, so it would be 4x squared over 9 minus 4y squared over 27 equal to 1. For part B, since E is 1/2 is less than 1, we know we're looking at the ellipse. The vertex would be at 0, -8, indicate that the vertices lies on the y-axis, and A is equal to 8. So I can look for the formula again. E is equal to C over A. E is 1/2. I know what A is. I can solve for C. Then I know B squared is equal to A squared minus C squared for the ellipses. From there, I can solve for B and all the information to write the equation of the ellipse now. Y squared over 64 plus x squared over 48 equal to 1. So one of the application problem in this section, the orbit of the planet Mars is an ellipse with sun at one focus. The eccentricity of the ellipse is given to me as 0.0935, and the closest Mars comes to the sun is 128.5 million miles. Find the maximum distance of Mars from the sun. So this shape would actually really help me to look at the values I need for the formula. And using the given figure, Mars is closest to the sun on the right, furthest from the sun on the left. So the smallest distance is A minus C. The greatest distance would be A plus C. Since A minus C is given to me as this figure 128.5, so C would be equal to A minus 128.5, and E is given to me, then we can use the formula E is equal to C over A. The only unknown here is A. You can solve for A. A would be approximately 141.8. C would be approximately about 13.3. A plus C would be then equal to about 155.1. So the maximum distance of Mars from the sun is about 155.1 million miles. The last thing we're going to do in this section is solve the system of nonlinear equations. The first one is x squared plus y squared equal to 4. The second one is 2x squared minus y squared equal to 8. We do use, for most part, elimination methods. Sometimes we can use substitution methods for these. So as you can see, if you look at the graph of the first one, this is a circle. And the second one, just by looking at this, would be a hyperbola. So if you have a circle and hyperbola, we can see visually where they intersect. So in this case, if you want to calculate that, we can use elimination method here. As you can see, the coefficient of y squares are opposite of each other already. So if I just simply add them up, I get x squared plus 2x squared would be 3x squared. 4 plus 8 equal to 12. Divide both sides by 3. You get x squared equal to 4. We get multiple intersections for these problems. X would be equal to plus and minus 2. So if x is equal to 2, we're going to substitute that in either of those equations and solve for y. So we get our points of intersection would be 2 and 0, negative 2 and 0, where you can see, if you graph these, you can see where these intersect. We could use a graphing calculator to find a point of intersections also. This would be another example to solving a nonlinear system of equations. So we can begin as with elimination method. In this case, if I just simply add these up, we can multiply the bottom row by -1. As you can see, x squared cancels, y squared cancels. And if I multiply the bottom row by -1, you can see I get minus x squared here, plus xy here, minus y squared, minus 6. So now if I add these x squared, y squared cancels, you get 3xy plus 1xy give you 4xy. And then you get 22 minus 6 would be 16. You can solve for y. So y would be 4 over x. Now I find the equation y in terms of x. The next step is to substitute that into the equation x squared minus xy plus y squared equal to 6. Because we only have two variables here, x and y. If I substitute for each y 4 over x, then I would have only one unknown, which I can solve for. If you substitute for each y 4 over x, a lot of this reduces. You get x squared, this x and x reduces to 1, you get minus 4. Here you get 16 over x squared, divide each term by x squared, and we have to factor here at this point. You could use a substitution method here, but that's simple enough to factor. And you get x squared minus 2 is equal to 0, and x squared minus 8 equal to 0. For the first one, we get x equal to plus or minus radical 2, or x equal to plus or minus 2 radical 2. Then we need to substitute that back into equation number 4 to find for x. So when x equal to radical 2, y would be equal to 4 over radical 2, which is 2 radical 2. When x equal to minus radical 2, y would be equal to 4 over minus radical 2, which is equal to negative 2 radical 2. So here would be my 4 point of intersections there. When x equal to 2 radical 2, y would be equal to radical 2. If x equal to negative 2 radical 2, y would be equal to minus radical 2. So we get 4 point of intersection. If you graph this, you can see all these points of intersection would make a lot more sense also. This would be the graphing a nonlinear system of inequality. So in this case, if I graph these to the graph of the inequality number 1 consists of, this would be an ellipse, and we need to shade which part of the ellipse is the solution by using the test point. Usually 0, 0 would be a good point, good test point. The second graph is a hyperbola with the horizontal transversal axis. You can look at the graph here. If you graph the hyperbola and the ellipse and use the test point, you can see the point of intersection would be what is shaded here. So this would be a solution to that.